Welcome to The Explainer. Today, we're going to dive into how scientists are basically building virtual labs, all to design, test, and perfect the microscopic machines of tomorrow.
Right? So here's the fundamental question, the big challenge in nanotechnology. We are talking about devices that are so unbelievably small, built on micro and even nanoscales. At that level, your traditional physical ways of testing things, they're pretty much impossible.
And these devices are called nano-electromechanical systems, or NMEMS for short. And you've got to understand, these are tiny, tiny machines with absolutely massive potential. They're revolutionizing everything from medical diagnostics that can spot diseases at a cellular level to the super advanced sensors in our phones and in spacecraft. But for these little devices to become as powerful and reliable as we need them to be, researchers first had to fix a really fundamental design flaw that was holding everything back. For years, a lot of these sensors were built using what's called a cantilever design. The easiest way to picture it is to think of a microscopic diving board, just a tiny little beam that's fixed on one end and free to vibrate on the other. And right there, that's the problem. Just like a real diving board, which bends and flexes the most right at the tip, a cantilever resonator's sensitivity isn't uniform at all. The vibration is way stronger at the free end. So a particle that lands there gives a totally different reading than one that lands closer to the base, and that leads to inconsistent, unreliable measurements. Not good. So to make a sensor that was actually accurate and reliable, engineers had to go back to the drawing board. They needed to completely rethink the geometry to get something that was uniformly sensitive across its entire surface. And here, you can see that evolution right in front of you. On the left, you've got the old cantilever design. And on the right, well, that's the ingenious solution, the pedestal resonator. It is a complete game changer. So instead of that simple beam, the pedestal design has this central platform, and it's suspended by 4 flexible legs. This is a brilliant change because it means the entire platform oscillates. It moves up and down as one single uniform unit. This super elegant shift in geometry completely solves that problem of uneven sensitivity. We're talking a variation of less than 4% across the whole surface. Incredible. Okay, so you've got this great design on paper. That's one thing. But how in the world do you actually test it and tweak it and prove that it works when the thing you're building is thousands of times smaller than a grain of sand and costs a small fortune just to make one? And this is where the hero of our story really comes in. Finite element modeling, or FEM. It is the key that unlocks our ability to actually design and test things at the nanoscale. You should think of FEM as creating a perfect digital twin of a physical object. It's this incredibly powerful method that lets scientists simulate exactly how a design is going to react to real-world forces. Things like vibration, heat, stress, all inside a computer, without ever having to build a single physical prototype. The whole process is really systematic. So first, engineers create this super detailed 3D model of the design, in our case, the pedestal resonator. Then, the software slices that model up into a fine mesh of thousands, sometimes millions of tiny little pieces. These are called finite elements. And finally, they apply virtual forces, tell the computer what the material is made of, and then just let it analyze how every single one of those elements reacts. Now this slide really shows you just how powerful this technique is. This load displacement curve basically shows how a material bends when you push on it. On the left, that's the theoretical curve. It's what all the math says should happen. And on the right, that's the result from the FEM simulation. I mean, look at them. They are a near-perfect match. It proves the simulation can accurately predict real-world physics. But FEM isn't just for testing if a design works. It's also this incredible tool for understanding exactly how and, more importantly, why materials break when you put them under extreme stress. To really push a material to its limits, scientists use a method called nano-indentation. It is basically what it sounds like. They poke the surface of a special coating with an impossibly sharp, diamond-hard tip to see just how much force it can take before it cracks or fails completely. So when they do this test in the real world, this is what they see under the microscope. You can clearly see the physical damage, right? The chipping around the edge, those cracks shooting outwards, and the delamination. That's where the coating has literally peeled away. But this only shows us what happened. And this is where the power of FEM becomes crystal clear. This is the simulation that corresponds to that physical test. The colorful map is showing you all the invisible stress fields building up inside the material, with red being the areas of highest stress. It reveals exactly where those cracks are going to form, predicting the chipping and delamination before it even happens. It doesn't just show us what happened, it tells us why it failed. And the simulation can get even more granular than that. It can tell the difference between different types of stress. So the vertical force, that's compressive stress. It's just pushing down. But as the simulation shows, it's often the horizontal shear stress that causes the real damage, the force that pushes sideways and causes the coating to peel right off. FEM lets us see all these distinct forces at play. So what you have is this amazing combination of clever new designs and incredibly powerful predictive simulations. And with those two things, researchers are just accelerating the development of next-generation nanotechnology like never before. And as the source material itself concludes, it's this constant feedback loop, between the virtual simulation and physical reality. That's what bridges the gap between a great idea on a whiteboard and a real functional device that can actually go out and change the world. So the key takeaway here is that simulation is totally transforming engineering. It lets researchers predict performance, rapidly test and fine-tune new ideas, literally see the invisible forces that cause things to break, and ultimately build better, stronger, and more reliable devices, and do it faster and cheaper than was ever possible before. And that kind of leaves us with this fascinating final thought to chew on. As these digital twins, these simulations become so accurate that they're basically indistinguishable from reality, what does that mean for the future of scientific discovery? What even is the role of the physical lab at that point?